Today I want to talk a little bit about molecular orbital theory, or MO theory, which is another way of visualizing bonding in nonmetal with other nonmetal compounds. So molecular compounds with covalent bonds, we can talk about molecular orbital theory. And this relates to, in other videos, we talked about valence bond theory. We've talked about kind of three-dimensional geometries. We've talked about covalent versus ionic bonds. There's a number of different bonding types. There's a number of different theories about why and how things bond together. This is just another one to help explain parts of our understandings about chemical bonds, which are complicated because they involve electrons, and electrons are complicated because of wave-particle duality. So recall that electrons, in kind of a simplified view, act as both particles, meaning that they have mass and they occupy space, and waves, meaning that they have energy associated with them. So when we talk about atomic orbitals, we're talking about three-dimensional mathematically derived regions of space where that electron most probably will be. And so when we're talking about the particle nature, we're talking about kind of a physical location. So that region in space that we're looking at. But the wave nature, we're talking about the energy. And the energy comes from the relation to the nucleus. How far away from the nucleus I am, the further away, the greater the potential energy that electron has. So the movement of electrons and the sharing of electrons has both a physical component to it and an energetic component to it because electrons are both. And so when we've talked about modeling theories in the past, we've mostly focused on the physical location of them. Are the orbitals overlapping? Are they in between two nuclei? Where are the electron pairs around a central atom? So that's a physical location. But in molecular orbital theory, it focuses more on the energy or wave nature of electrons. So we get into the quantum mechanical kind of behavior of electrons, and that helps to explain why certain things bond together and why other things do not from an energetic standpoint. So in order to talk about that, we need to remind ourselves about waves. So when waves interact, they can interact with each other constructively or destructively. And I like to think about it as ocean waves because I would love to be on a beach somewhere right now. And if you picture ocean waves, you've seen sometimes when ocean waves will roll in and then another batch rolls in, and then when they roll in and they hit the same spot, then they get bigger, right? And that's good for things like surfers, for example. They love when there's constructive interference of ocean waves. And you also will see that they'll combine together and waves are rolling in, waves are rolling out, and there's these flat spots. And it always looks a little bit funky when the ocean is flat in places, but it's totally flat because those waves have interfered with each other destructively. So we can kind of talk about this from a qualitative standpoint, from a conceptual standpoint. So I'm not going to actually put numbers to any of these things, but just from a kind of an ideas standpoint. Constructive interference is when if I have a wave and I add another wave to it, so if we're picturing like waves on a beach and they roll together, then when I add them together, if they're both headed in the same direction and they hit in the right way, then they're going to interfere in an additive way, meaning that they get bigger. So the sum of the waves, because they're constructively interfering, mean that the size of both increases. We say that the waves are in phase with each other. Now, destructive interference, of course, is the opposite. So if I have one wave that rolls in and another one that's going in an equal and opposite kind of way, I add them together, they're going to interfere destructively. And we'd say that these waves are out of phase with each other. So these out of phase waves, when we add them together, give me nothing, right? So I either end up with something that's quite large, or nothing, or somewhere in between. And this is exactly in phase, exactly out of phase. You can have other combinations of that, but for our purposes and our understanding of this model, let's just kind of focus on the in phase, out of phase. Okay. So far so good. Let's relate this to what we're talking about with atomic orbitals then. So recall that valence bond theory says that when I put together two orbitals and they have overlap, so long as there are fewer than 2 electrons between those two orbitals, or 2 or fewer, then the overlap results in a chemical bond. So that overlap between atomic orbitals is a covalent bond. It allows for sharing of electrons, and this is just kind of the model that we use to understand bonding. Overlapping orbitals, this would give us what is called a sigma bond, which means that it's in alignment with the bond axis, if we're thinking about this kind of on a three-dimensional coordinate system. So bond and overlap in the line of the bond axis gives me a sigma bond, and the same is true for MO, but because we're focusing on the wave nature of electrons and not their physical location, then there's really two possibilities when this overlap occurs. Because electrons are waves, then they can either interact constructively and interfere with each other constructively, or they can interact or interfere with each other destructively. So I have now an overlap between orbitals that either results in bonding with constructive interference or what they call antibonding for destructive interference. So if we're visualizing that, if we have an overlap between the orbitals and the wave nature of the electrons interacts in such a way to where they interfere constructively, then the best possible outcome for those electrons is for them to be situated in between these two positively charged nuclei. So if I have 2 plus signs here, and the electrons have a choice to be anywhere kind of within the realm of the atomic orbitals, energetically speaking, the best possible way, if they're all in phase here, is to be right between those 2 nuclei. Because now it's feeling the pull from each of those positively charged nuclei, and that's a good thing from a kind of magnetic energetics perspective. So electrons between the 2 plus signs is a great thing. This results in bonding, and that's one option. The same thing could happen. I could have the same 2 orbitals, but if my electrons interact destructively or interfere with each other destructively because of their wave nature, then the electrons are going to be on opposite ends, and what we end up having is kind of these 2 nuclei from these 2 atoms that are looking at each other and hating it, right? Because I have 2 positive charges. We're pushing these things together, and these 2 positive charges want to naturally repel. So this is not a friendly thing when we're trying to think about sticking things together, right? You're putting together 2 sides of they're 2 of the same sides of a magnet, and they're naturally wanting to repel each other. So we call this antibonding. Now the thing about quantum mechanics is, because electrons are waves, because we're talking about probabilities, because we're talking about electrons, and because quantum mechanics is wacky, then both of these possibilities are possibilities. Both of them are actual things that could happen. It's just that this one is more likely because it results in a lower energy situation. So this bonding, this constructive interference, is lower energy, and this is higher energy. And the universe in general likes to be at the lowest energy possible. That's that idea of a ground state, right? So things want to be in the lower energy configuration that they possibly can be in, and it would take some doing to put them in a situation where they're higher energy, right? I'd have to put energy in order to make that happen. Or we would find that there are elements that are just not going to do this because it's too high energy. So I'm trying to put 2 elements together that don't want to be together. Bonding versus antibonding. Let's look at the first 2 elements on the periodic table as examples of this. So let's think about the energy. Let's look at H2, which hydrogen, of course, is number 1 on the periodic table. Each hydrogen has 1 electron, and we think about the bond between these 2 as this shared pair between them, so we have a full 1s orbital. Now, all of that is stuff that we know because we know things about other models for how we put these things together. But if we didn't know this, then we could use MO theory, we could use molecular orbital theory to figure out whether or not the hydrogens would form a bond. So let's do that now. When I take these 2 1s orbitals and I overlap them, then in the middle here I'm going to put my MO orbitals. That's redundant. Molecular orbital orbitals? No. MOs. I'm going to put my MOs here in the middle. So my MOs are going to be the options that happen when I put these two things together. What happens when I interfere constructively? Well, I end up with an energy that's lower. It's a sigma bond because we're in the line with the bond axis. So this is what is called my bonding orbital. And again, sigma indicating that I'm in the bond axis. And the other option is when I put these things together, my 1s orbitals, I'm going to have a higher energy than either of them on their own. It's still an overlap within the bond axis, but I have that weird kind of electrons on opposite sides piece that we just saw on the prior page. So we call this a sigma star orbital, which is an antibonding orbital. Now this is going to be true for any interaction between the orbitals. So when I put them together, there's going to be two possibilities, something that's constructive and something that's destructive. Now if I have more than one orbital type, I'm going to have more than one overlap type, and that those different overlaps are going to have different MOs, but we'll get into the details of that in another separate video. We're just going to focus on hydrogen and helium in this one. So now I can fill in these orbitals with my electrons that I have that I'm bringing in from each of my elements. So each of my hydrogens has one electron. So my one electron here is going to go down to my lower. So this one comes here, and then this one comes here. So each of these electrons is going to go down to a lower energy state. And that's what it would want to do, right? It wants to be at a lower energy. So the choice is I could stay in this 1s, which is higher energy, or I could share this pair and be lower energy in this overlapping situation that I have in this MO. So that's going to be the choice every time. Lower energy always wins. And now I'm out of electrons. So I have one electron from each. I've filled them in here, and now I'm good to go. So I have 2 electrons in a bonding orbital, which means that I have one bond. And we can calculate this with what is called the bond order. So the bond order is equal to the number of bonds in between those atoms. So in our diagram here, how many bonds are going to be in between these two hydrogens? And the way that we calculate that is 1/2 the number of electrons in bonding orbitals minus the number of electrons in antibonding orbitals. So for this calculation, then, if we're doing the bond order for my H2, then I have 1/2 times the 2 electrons that are in bonding orbitals minus the 0 that are in my antibonding, which gives me 1. And that's the number of bonds that would form in between my 2 hydrogens. So it's just confirming what I already know with my other models. Okay, now let's look at how this plays out with something like helium. Let's look at helium-2. Now if you look at that and you've studied any chemistry, that probably makes you cringe a little bit. You're like, diatomic helium, that doesn't even make sense. Well, let's talk about why it doesn't make sense by putting together the MOs. So I'm going to have the same situation here. I have a bonding and an antibonding. My bonding being lower energy than either of the initials, and my antibonding being higher energy. Now when I fill in my electrons for each of my heliums, now I have 2 electrons in each. So I have 1 from each here. And then I'm going to put the other ones here, 1 from each here. So I have 1, 2, 3, 4 total coming in. So I need 1, 2, 3, 4 in my MOs. So I'm good to go. Now if I'm looking at the bond order from this, I would say that my bond order is equal to 1/2 the number of electrons in bonding orbitals, which is 2, minus the number of electrons in antibonding orbitals, which is 2. So that's 1/2 of 0, which is 0. That means that there is no bond that forms between these, and this would not be a valid structure, right? This is not an energetically favorable structure because of the way that its MOs line up and the electrons that we're bringing in. If you have any questions on this, I'll do other examples in a future video, so check that out. Otherwise, I'll talk to you again soon.